Okay, questions? No questions? All right, let's talk about Diels-Alder reactions then. So for the Diels-Alder reaction, that's going to be the reaction of a diene, a conjugated diene, and an alkene, like we did in lab this week, or last week. So in terms of writing the structure of the diene, if we just take a normal diene, I usually like to number it from 1 to 4 like we did on Monday. The alkene will be carbons 5 and 6. So that what you do is you end up making a 6-membered ring with a double bond, so you end up forming a cyclohexene as your final product. So both Otto Diels and Kurt Alder won the Nobel Prize because not only did they form a carbon-carbon bond, they formed 2 in a ring. And so pretty much everybody that developed reactions in the late 1800s, early 1900s, that formed carbon-carbon bonds won Nobel Prizes. And Diels and Alder was Diels' student, I believe, in Germany. And Kurt Alder became one of the early American organic chemists that was famous. Because organic chemistry was up till that point a German. It was a German discipline. So, in terms of the electron movements, we can take the double bond between 1 and 2 and move it to 3, the bond between 3 and 4 to form the 4-6 single bond, and then between 5 and 6 to form the 1-5 single bond. And the arrows can go in different ways. Since basically everything occurs at the same time, it doesn't matter which way the arrows go. The transition state for this reaction is basically going to look like this. We're going to have the formation of the 1, 5, and 4-6 bond, and then we're going to have partial double bonds throughout the rest of the molecule. So that would be the transition state. And the way this reaction works is that if you have a double bond, a conjugated system, those are all the p orbitals of the pi bonds. And what happens is that the spacing between carbons 1 and 4 is just perfect to overlap the 2 p orbitals of the alkene. Okay, which then allows these orbitals to overlap, and then we form the cyclohexene. So this is a concerted one-step mechanism. So that's the basics. And if you follow through on the 1 through 4, 5, and 6, it really just depends on what's attached to each one of those carbons to form the product. All right, so that's the basics. Now, what are the rules for Diels-Alders? Well, they're in the PowerPoint handout that's online for the that goes with the video. But let me see if I can remember the 3 of them. Rule number 1: you need to have the S-cis conformation for the diene. What does that mean? Well, for the diene, you have a sigma bond. And so when we talk about S-cis, we're talking about rotating around that sigma bond so that the double bonds are either cis or this is the S-trans. And the spacing is only good to do a Diels-Alder if it's in the S-cis. If it's in the S-trans, carbons 1 and 4 are too far away from each other to sit right on top of the alkene. So the conformation for the diene has to be S-cis. And the problem that we sometimes have with an S-cis conformation is that if we looked at the hydrogens that are attached, they would look like this. So these two hydrogens would be really close in space. So if we have a non-cyclic diene, we sometimes have to heat the reaction in order to get it to go from the S-trans conformation, which is more stable, into the S-cis conformation, which is going to be less stable. So sometimes to make this happen, we have to heat the reaction. Now, is that why we heated the reaction in this week's experiment, where we had to reflux it for 30 minutes? So we had to reflux this reaction partially, because what we were doing in lab was we were reacting this molecule, which is sulfolene. And so the sulfolene then, when you heated that, you would end up with this pair of electrons going there to form the double bond, forming the other double bond, and then going into the sulfur. So we ended up making SO2, which showed up as kind of the white gas at the beginning, and then that freed up the molecule to form butadiene. Butadiene is a gas. So if we were going to do this, if we were going to do the reaction, the Diels-Alder reaction, any of those with butadiene, the problem is butadiene's a gas. So, and working with gaseous reagents isn't easy. Now, you're using butadiene. If you drove here, you use butadiene, because butadiene is the raw material that's used to make polybutadiene, which is rubber. So your tires are made of polybutadiene, and your tires are not made of natural rubber, right? When rubber first started to be used as a product, it almost killed all the rubber trees not in the U.S. U.S. didn't have rubber trees. So they had to come up with a synthetic way of making it, and that was using butadiene to make polybutadiene and other things. So the butadiene, what we did was we heated it, we cracked it open, and then that molecule had to be heated so that it would go into its S-cis conformation and react with the alkene.
If the trans conformation is more stable, why would heating it make it flip anyway?
Well, because it gives it more energy to overcome any barriers. And once it goes into the S-cis, then it immediately reacts. I mean, in order to make a molecule move from a less stable or more stable into a less stable, that means it has to absorb energy. That has to be an endothermic process. So like anything else, there's an activation barrier. You start with S-cis or S-trans, and you have to overcome some activation barrier to get to, let's say, S-trans or S-cis.
Energy that's being stored within the molecule that forces it into its conformation.
Yes, the molecule has more energy. I mean, what you have to think of is kinetic energy. So when we raise the temperature, we raise the kinetic energy of the system. The kinetic energy, molecules transfer energy as they're smashing into each other. And so you might have a real high energy molecule smash into the butadiene, and then all of a sudden it switches. And then it reacts. So that's why we have to heat it, because if we don't, we're never going to be able to get the molecule into a higher energy conformation. But how it absorbs energy is primarily through collisions with other molecules. That goes back to general chemistry, the the Boltzmann distribution and all of that. So that's part of the reason why we had to beat it. The big part was, if I can't crack it, I can't make butadiene and I can't do the reaction. So just so you know, if you ended up with a product that looked like it was a little wet, because it looked like it was not really crystalline but kind of gooey, you may not have cracked it all the way. I only have experience twice with this reaction, but when we did it last spring in the micro scale version, which some of you did, I think people had a hard time getting it to crack. So then I modified it and used a different version of that experiment over the summertime, and it worked great, and that's what we used. So if you saw that, you might, in your IR, you might see that you have a little bit of uncracked sulfonylene. And that just means you didn't make butadiene, so you couldn't have made the product. So that's rule one. The diene has to be S-cis. Okay. Now, if you put methyl groups here, that might be even more difficult to get it to work. So it's really going to depend on, if it's an acyclic system, it's going to really depend on these groups. Even if they're hydrogens, they're going to be butting up against each other. So that's rule number one. Rule number two is that the stereochemistry of the alkene is preserved in the product. So that means if the alkene is cis or trans, those two groups are going to be cis or trans in the final product. So let's say I'm reacting my butadiene with, let's say, this molecule, which would be some sort of acrylonitrile type molecule. Now, is there anybody thinking this reaction won't occur? Hopefully not. Now, sometimes people get confused with the S-cis rule, and they say, but this isn't cis, so I won't get a reaction. Remember, the S-cis is over in the diene. This stereochemistry, whether it's cis or trans, is okay. It's just that when you make that final product, in this case, the CN groups are going to be trans. So the trans stereochemistry of the alkene is then carried over into the trans stereochemistry of the final product. And so whether it's cis or trans, those two groups will be cis or trans in the final product. So the alkene can be either. Now, one of the things in terms of the textbook is, because I have to go through and I may remove some chapter 19 questions that have to deal with like molecular orbital theory. Because it has, for instance, the regioselectivity. So, for instance, if you have like an OCH3 group there, and you had, let's say, like one CN group on this side, what's the major product going to be? Is it going to have the OCH3 and the CN on the same side? Are they going to be on opposite sides in the final product? And we're not going to get into that level of detail. It's not based on sterics. It's not based on stability. It's based on what's called molecular orbital theory or frontier molecular orbital theory, which your book goes into, and I'm not going to. So we're not going to be concerned about these kinds of reactions, but it's totally based on that. What is what the optimum Diels-Alder has what's called electron withdrawing group in the alkene and an electron donating group in the diene. That's the optimum situation. Now, if you're looking going, well, how do we know that? We don't. We will when we talk about benzene molecules Friday-ish, Monday-ish, after break-ish, right? Because then break is after next week. It's all this sigh about that. I hope it's here, comes here sooner than later. We'll talk about what electron donating and withdrawing groups are. So we haven't really talked about that yet. So it's kind of hard to, it would be hard to explain this in those terms, but you may see that in the book. But I have to go through and tell you what problems you don't have to do, or which problems I guess I'll remove from your score. But it'd be better if I just told you which not to do to begin with. So the real stereochemistry that we're going to talk about is this. Stereochemistry of alkene being preserved in the final product. Josh?
I was curious if you predict that the benzene reactions will be on the exam.
Only a couple of them. Yeah, only a couple of them. We weren't going to get into a lot of electrophilic aromatic substitution. That'll come after break. So that's the stereochemistry part that's important. And it doesn't matter whether you write the CN group in this case with a bold or dashed wedge. So there's two possible products. The relationship between those two products would be that they are
They're the same.
they're not the same. Any chiral centers? Two. What about this chiral center? Same or opposite? Top chiral center, same or opposite? Give me an answer.
Opposite.
Good guess. Opposite. Bottom. Opposite. Two chiral centers are opposite in both molecules. That makes them enantiomers. Which makes sense. Because remember, our rule of making a chiral product is you need a chiral reagent. There's no chiral reagent. So we would expect to get a 50-50 mixture of these two enantiomers. So it doesn't matter how you write the CN, whether it's just one bold, one dashed. Okay? So that's rule number 2 about stereochemistry. Rule number 3 has to do with cyclic alkene or cyclic dienes. Now, when you have cyclic dienes and you react those with a cis alkene, you get what's called the endo product. 100% endo versus 0% exo. Yeah, and in order for the alkene to be by saying it's cis, it has to be disubstituted. So we'll do a couple examples here. Okay, so it's a cyclic diene plus a cis alkene. So a cyclic diene, how about let's use a simple one, cyclopentadiene is a cyclic diene. Now, cyclic dienes react a lot faster than non-cyclic dienes because when you make a cyclic diene, you pin it into its cis conformation. So a cyclic diene automatically has to be S-cis. Another one that I use quite often is cyclohexadiene. Both of these have the double bonds pinned so that they are S-cis. The butadiene is the cyclobutadiene or cyclopentadiene here. We used to use that for our Diels-Alder reaction. At least when I taught second semester lab, we would use it. I'm actually okay with the substitution, but when I taught this, we always used this product. And the problem was that cyclopentadiene, has a tendency to react with itself, where one of the molecules acts as the diene and the other one acts as the alkene. And so in the bottle, you end up making what's called dicyclopentadiene, which is not a diene, so it will not react. So what you end up having to do was to take the dicyclopentadiene, put it in a large distillation apparatus, and slowly heat it so that it cracked. And when it cracked apart into these two cyclopentadiene molecules, they would distill over, and you would collect them in a round bottom in like dry ice. So that took a couple days to get enough for lab. And then if you let it sit at room temperature, it would go back to dicyclopentadiene. So when we use a sulfoline and we crack it, it's okay. It's a good alternative. So these molecules will react with an alkene, but let's take this stepwise. So I'm going to take my cyclopentadiene and I'm going to add to it an alkene. Not cis yet. Okay, so I've got my 1, my 2, my 3, my 4, my 5, and my 6. So when I do that, I'm going to end up with a 6-membered ring with a CH2 attached to both carbons 1 and carbon 4, because that's what this CH2 is attached to. So that's one of the ways that I can write it. And typically when I write that, I'll put bold wedges on it, because this 6-membered ring structure looks like this. That's what it looks like sideways. And if we went back to last semester remembering how to number bicyclic systems, that would be a bicyclo... Oh, actually, I didn't get the right name this morning. It would be as bicyclo-2,2,1 heptene, and my double bond would have to be in... It's a 2-heptene. Because the double bond is on carbon 2. Right. So we're not going to worry about the naming right at the moment. But that's a bicyclic system. So the original 5-membered ring sort of came from this part, and then that's where the two carbon piece went. Now the reason I draw this is because I need to explain what the exo and what the endo products are. So I'm going to rewrite that over here. So there's two equatorial positions coming off of that ring, and then there's two axial positions that are down. So when I think about, well, which one's endo and which one's exo, I think about what exo and endo mean. Right? Exoskeleton, endoskeleton. Right? One's outside, one's inside. I like to think of this molecule as having this, being like in this cylinder, kind of, where the groups that are pointing outside the cylinder are the exo positions, and the ones that are kind of in the cylinder going down are the endo positions. It's kind of how I remember which one is which. So the rule 3 is that if we took cyclopentadiene and reacted it, let's say, with our, let's go ahead and react it with our maleic anhydride from lab, it's cis. And so what would happen is, in our product, we could write the product one of two ways. Notice that the bridge here, this is called the bridge. The bridge and the endo positions are opposite. So that means over here, if I wrote my bridge with a bold wedge, my CN groups would have to go on a dashed wedge. And then there'd be a double bond. So you can write the product this way. Now this way of drawing is if I'm up here, looking down on the molecule. The bridge is pointing towards me. So if the bridge is up, the two groups are pointing down, and that's the endo product. And that's the only product that's formed when you react a cyclic diene with a cis alkene. Okay, so that's the endo product. We never get the exo product in this reaction. Although actually when I was going through and I was modifying the Diels-Alder reaction, I did find a paper that said you could get the exo product, which I thought violated like all the rules of quantum mechanics, and the world was going to end. Because we always talk about, well, you never get the exo product. We'll still say you never get the exo product, but apparently the reasoning for this is in frontier molecular orbital theory. These are what are called Woodward Hoffmann rules. Both of those guys won the Nobel Prize for various things. It was Robert Woodward, who is one of the giant like synthetic organic chemists. He basically made like everything. They isolated something from some bug. They synthesized it. Smoked like a fiend. There's not a picture without him with a cigarette in his mouth. I think I have a signed photo of him in my office, and it has the prerequisite cigarette. And then wrote Hoffmann, if you've ever seen the PBS series, it's really old, on chemistry, where they go through all the different, they might have shown it to you in high school or even grade school, like different things. He narrates that. He came to Cleveland once and gave a talk. I gave both of the books that I had by him to one of my colleagues, and she took it down and had him sign both, and then appropriated one of the books for herself. So I guess we don't, because he never signed the one she took. So I have a sign book from him too. But they had to figure out, I have a pretty boring life outside of this. So that's one of the few things that I do. So the idea is, this isn't about kinetics or thermodynamics. It's all about these orbitals. And that would be for an advanced organic class, which we're not offering this year. Maybe sometime in the next 15 years we'll offer that again, but that's the last time I taught it, was talking about frontier molecular orbitals. So this is called the endo rule. So you always get the endo product. So whether you write the endo product, and I could write this one like this, with now the it's kind of hard to draw that ring, but the key thing is those hydrogens are equatorial. So the C double bond O, that 5-membered ring would kind of hang out down to the bottom, which is not what I wrote here. Why did I do that? It would have been easier to write the C triple bond ends. Okay, so that's rule number 3. Whatever is a cyclic diene with a cis alkene, you get the endo product. Which of course leads to the question that, what product do you get if it's trans, if the alkene's trans? Which we can do. So let's take this one. So let's do cyclohexadiene. Now the cyclohexadiene, instead of having a CH2 as the bridge, is going to have 2 CH2s as the bridge. So if we reacted it with a trans alkene, like this, the reaction would still go. It's just that it's not going to form an exo or an endo product, because the exo and endo products are defined as both of those groups being cis. So we would get, if we wrote the product out this way, we would have our double bond, we would have our CH2 group, our other CH2 group, then bonded to carbon 4. And then one of the CN groups would be on a bold wedge, and the other one would be on a dashed wedge. And that's not exo or endo. Exo or endo has to have both those groups being the same, being cis. So that's what the product would be, and it would be classified as neither endo nor exo. That on its side would look like this. So one of the CNs would be axial, and one of them would be equatorial. So I did put some practice problems on doing Diels-Alder reactions in today's folder, but I haven't green check marked them yet, which I will do after class. And don't worry, I told the morning class I would check mark them after their class, and so eventually I'll get around to it sometime in the next hour or so. But that's Diels-Alder. 6-membered ring, cyclohexene, whatever the groups go 1 through 6, and the stereochemistry of the alkene has to be preserved. And in these cyclic reactions, if the alkene is cis, it goes into the endo position only. And so that's sort of what we did, except we didn't use a cyclic alkene. Ariana?
So just to clarify, if it's a trans alkene, it's neither endo nor exo.
Right. And the endo or exo would have to have these two groups being cis. If they're trans, we don't have a name for that I know of. Right. If these two groups are trans, it doesn't have a name. If it's endo, they're both opposite the bridge in terms of bold and dashed wedges. If they're exo, it's the same boulder dash that you have with the bridge.
Oh wait, that bridge is 50-50. Is it just trans or is it trans?
No, the bridge. This bridge is above the ring,
Yeah.
and so if it's exo, both of these groups would be bold. They would be on the same side as the bridge. So the way we define it is, here's my bridge, here's on the same side. And then there's my bridge, and then axial down would be opposite. And if you don't like my drawings of it, we can go to that one, which was the one from the notes that are in the folder that go with the video that I'm not sure if people watched or not. It's fine, honestly. Well, I don't know if at some point it'd be helpful, but because it's going to be a lot of the same stuff, but it's there. At least look at the book. So that's where that's how it's defined. It's actually not defined on the bridge. It's defined on the side where the double bond is, but that's too much detail. Okay. All right, so that's all for Diels-Alder then, other than practice. One sort of last thing that we want to do with the allylic position that I didn't get a chance to talk about on Monday is, what if I had an allylic chloride and I wanted to react it with hydroxide? I wanted to do this SN2 mechanism. Do allylic chloride, does the allylic position react faster, slower, or the same in an SN2 reaction as just like a normal primary position? We already know that this position, which needs to do this, truly to be the allylic chloride, we know that the allylic chloride reacts faster in an SN1 mechanism because that forms, when you lose the chlorine, you form a stable allylic carbocation because it'd be primary allylic with two resonance structures. What about its effect on SN2? Well, let's write the transition state. So I would have the oxygen coming in and attacking the carbon, kicking off the chlorine, and then I would have my trigonal bipyramidal SN2 transition state. What would the charge on the hydroxide be? Delta minus, chlorine, delta minus, carbon. What do you think it should be? It's in between two delta minuses. Let's make it delta positive. It's not going to be delta minus, because having three delta minuses, and then you also would say, but wait, how's this hydroxide coming in and attacking that carbon? Because that carbon had to be delta plus to begin with. Now, we haven't focused on that delta plus carbon. We haven't even written delta plus before. I know some of you have. That's fine. So now I put a double bond here. What does that do to the, and then there's two H's. So what do you think that does to the transition state energy? Does that double bond stabilize that delta plus Does it destabilize it? Does it have no effect? Stabilizes it? The same way it kind of stabilizes a full-blown positive charge. So that double bond will stabilize that delta positive charge. And what it will do is it will lower the transition state energy, which in turn lowers the activation energy, which in turn makes the reaction go faster. So allylic halides will undergo faster SN2 reactions than if it wasn't allylic. And it all has to do with the stabilizing of this transition state. So I think that was the last thing in the diene, or in the alkene diene chapter that was left. Except for doing some mechanisms on 1,2 and 1,4 addition. And since I got tons of time, let me just ask a question, because I didn't get a chance to do this morning, and somebody came up and said, you said, here, I'll tell you exactly what they did. Because they had started on the practice problems, which I only posted at like 10 o'clock last night. I don't know. It's a sad existence. But here's the molecule that I gave. So here's 1, here's 2, here's 3, and here's 4. It's like Groundhog Day. Almost 7 days a week. It's okay. Don't worry. Don't worry about me. You'll know when I go off the deep end. You'll know. You'll probably be one of the first ones to know. Okay, so here's a practice problem. Where am I going to add? Which carbon am I going to add the H plus to? So this is a symmetrical diene. So that means adding to 1 is the same as adding to 4. Adding to 2 is the same as adding to 3. So really my question is, with what I said on Monday, which I said that, I guess I said you'd add the H plus Markovnikovs, according to Markovnikov's rule. The broad definition of Markovnikov's rule, where should the H plus go? 1 or 2? 1? Okay, I like that answer. So in the broadest definition of the Markovnikov's rule, we want to form the more stable carbocation.
But I thought you have to add the H's to the carbon with the most nitrogen.
Okay.
So wouldn't that be 2?
Okay.
Both of them are going to be secondary. One of them's
Let's do it. Let's add to 1, let's add to 2 and see what happens. So let me add to 1. So there's adding to C1. And there is the addition of the H plus to C2. What did I also say on Monday in terms of the addition of the H plus? I don't remember saying that. Always add the H plus to the end, to carbon 1 and carbon 4. Did I say that on Monday? Okay, good to know. Good to know that you're not helping. You're not helping things. It is. So which one of these two carbocations is more stable? The one on the left or the one on the right? How many people say the one on the left? Just be brave. The one on the right. It's the one on the left. Okay, so right now, I've got a secondary carbocation versus a tertiary carbocation. Can I do anything to this molecule over here, this carbocation? Any additional resonance structures I can draw? Any additional resonance structures I can draw over here? Yeah, so let's go ahead and do that. What did I get in my resonance structure? I formed a tertiary carbocation, right? So on Monday, whether I said or didn't say, I'm going to say now, we always add the electrophile to carbons 1 or 4 to the end. We never add in the middle. And the reason we do that is because we want to do Markovnikov's addition. But we don't want to do strict Markovnikov addition by the number of hydrogens. We want the broader, more generous Markovnikov rule, which says that I'm going to form the more stable intermediate. And in this case, the more stable intermediate is going to be the two resonance structures versus just the one. Because if you were concerned about a secondary carbocation versus a tertiary carbocation, look what I just made. I just made a tertiary carbocation, which now ties me with C2, but what do I have additionally? An extra resonance structure. So we always add to the end, because that additional resonance structure is always going to give us the most stable intermediate. Okay? And that's what you want to think about, because the molecules that I'm giving you for homework problems that you'll have to come up and get are ones where the double bonds are like this with two methyl groups there. And I think it's another 5-membered ring where the two methyl groups are in the middle. So when you start your homework, when you start these take-home quiz problems, always add your H+. You're adding H+ and H2O to these. Add the H+ to carbons 1 or carbon 4. Now, when I unclick well, actually they already unclicked because somehow she had a printout of the practice problem. So they're already available. If you want to do a practice problem and look at the narrated answer key, there are several of those in the folder for today. You can go ahead and do that, and then you can tackle. Hopefully I didn't put up the same exact problem. And if I did, I should never said what I just said. Okay, so here are the take-home quiz problems. They're also online. You can come up and grab one of those. I'll return and turn in your quiz problem from the other day. They're due today as well.
Oh, sorry.